Hello everyone, and I'm going to talk about our recent work on optimal asynchronous validated Byzantine agreement, which we call a Dumbo-MVBA. And I'm Qiang. This is joint work with my students Yuan and Zhenliang, and also my colleague Grace. The blockchain has been popular recently, but the scientific problem behind is the consensus problem, which has been studied by the distributed computing community for almost 40 years, in particularly the PODC community. Over the years, there are many related notions have been proposed, like atomic broadcast, Byzantine fault tolerant, and state machine replication. They essentially talk about the same thing. So the definition of the problem actually is quite simple. A bunch of parties, each of them have some input. They communicate, they want to reach agreement to a digital log, now sometimes called the digital ledger. A common definition of consensus requires consistency and liveness. So consistency essentially requires all honest guys' ledgers are essentially the same. While for liveness, they require honest guys' input will be recorded sooner or later. So two classical flavor of the problem is Byzantine agreement and atomic broadcast. As we all know, Byzantine agreement is a one-shot protocol that every party have an input, execute the protocol will output a common output. And the validity normally means if the honest guys input are the same, they will output that value. Otherwise, they might output some bottom. While atomic broadcast is essentially the same as the consensus definition, and we can view it as a continuous version of Byzantine agreement. One simplistic view is that we may directly do a sequential composition of Byzantine agreement to get atomic broadcast. This view actually is true in many cases, with one catch. In the asynchronous setting, in order for this simple reduction to work, actually we require the Byzantine agreement to satisfy strong validity, which means even if the inputs of those parties are different and they have to output one of the honest guys' input. And this is critical for the liveness property of the reduction of atomic broadcast. And unfortunately, the Byzantine agreement with such kind of strong validity is extremely difficult to get. The complexity is astronomically high. For this reason, in the seminal paper of Cachin et al., they proposed a nice notion called validated Byzantine agreement. Since now we know BA with strong validity is too hard to get, we might want to consider something weaker. While validity here only requires the output to satisfy certain predicate, while this means the output of the protocol could even come from a malicious party. Interestingly, this MVBA protocol still enables the simple reduction to atomic broadcast in the asynchronous network. In the paper, they show a very nice reduction, nice and simple reduction that while some intermediate protocol called the asynchronous common subset, which essentially requires everyone to output the common subset of all their input, then they can directly do the sequential composition of this ACS protocol to get the atomic broadcast. And in the same paper, they also gave a construction to this MVBA protocol. So I'm not going to explain this fancy protocol in 1 minute, but just have a quick look of the protocol. You can make an intelligent guess that this complicated information flow might not give you an extremely efficient protocol. And indeed, the major problem in this domain is that over the years, the security has been pushed to almost the strongest, and we can have security in asynchronous network, and even adaptive security now become reachable over the years. The major open problem left, an obstacle, is about efficiency. In particular, the atomic broadcast protocol we get from Cachin et al. Actually incur a cubic communication complexity. So in the number of players, communication complexity means total number of communicated bits. And also this is the same for the underlying MVBA protocol. If we take a closer look at the efficiency metrics of the Cachin et al.'s protocol, we can easily notice an uncubed term in the communication bits. Another important metric is time means expected the number of rounds, and message complexity normally means the number of communication channels need to build. And this two complexity actually was quite okay in Cachin et al.'s paper. Since this problem been there almost 20 years. In some recent breakthrough of Abraham et al., actually in last year's PODC, they finally removed n-cube term. That's great news. But you might also wonder why I put this detailed calculation of the formula here. If you take a closer look for a few more minutes, you might wonder. And there's an efficient coefficient in front of the n squared term, which is the input number of bits, which is L. What if these input bits are not so small? Essentially, what if the inputs of the players are not too short? This actually is very relevant in the original motivation from MVBA to atomic broadcast. So in the Cachin et al.'s paper, they show a very simple reduction from ACS to MVBA, that essentially every player multicasts his value to everyone. Then after a while, every player is going to have a vector of values. Now those players will use this vector as input to invoke MVBA to select one of the vector as their output of the common subset. While the predicate is very easy, simply check whether the vector indeed contain enough inputs from different parties. The important message delivered in this reduction is that when you use MVBA to construct atomic broadcast, actually when MVBA is invoked with input a vector of n elements. So the input length already is linear to number of players. And if we work hard to get the calculation, we'll be able to notice the surprising fact that actually the Ln squared term becomes cubic again. And this term actually becomes dominating. A very bad message from this observation is that the question about reducing communication complexity of the atomic broadcast actually remain open. And more concretely is the MVBA protocol with moderately large input size remains open. And in this work, we fill this gap and give a complete characterization of this open problem. And in particular, we continue shuffle another vector from the Ln squared term. You might wonder why don't worry about lambda n squared. Well, when L is moderately large, actually the dominating term will become Ln. Of course, we want to do this preserve all other efficiency. In particular, we give two protocols. One is more efficient reduction to binary agreement, and another one is actually our MVBA extension, which we will be focusing more on in this talk. So before we move to the details of how we get the communication down, let's take a quick look in the existing protocol. Where is the major communication cost? So in Cachin et al.'s paper, protocol, there are several phases of a message broadcast. In particular, one phase already broadcasts a bit vector with length n. Already this phase incur n cubic communication, but still, even if we can get rid of this cubic phase, there's still the beginning at the end, there's a message broadcast already incur Ln squared terms because everybody sends message to everyone. And if we look at Abraham et al.'s protocol, even though the protocol structure is quite different with Cachin et al.'s protocol, but they also have common phases of message broadcast. So this bunch of message broadcast, again, already incurred the communication complexity of Ln squared. So after very, very quick look at the existing protocol, we can actually make a very simple observation. So there always exists a phase that everyone sends its input to everyone. While this might sound very simple and a natural step, but unfortunately, if you think very, very hard, you will be able to figure out that this step alone already incur a communication complexity with Ln squared. Quite depressing. But if you continue to think very hard for a few more minutes, you might be able also to observe this step seems actually quite unnecessary, because at the end of the protocol, only one output will be output by the protocol. why bother to keep everyone else's input? So with this simple observation, immediate idea is, instead of multicast everybody's input to everyone, why not let them just do dispersal? While information dispersal indeed sounds very simple, and we still need to enable them to make sure they can recast a consistent version at the end. But luckily, this very simple observation indeed enable us to develop into a workable solution. But we need some effort. So we propose a new primitive called asynchronous provable dispersal broadcast. So it has two phases. First phase is dispersal. A sender takes its message or takes its input and disperse to everyone. Everyone gonna get a share, and with some auxiliary data. While this share and auxiliary data must be very short. Well, interestingly, there's also recast phase. Instead of recast by the sender alone, actually we can enable everyone, or actually all players, to recast the value. And we're going to insist on the property called recastability, in the sense that if the sender is honest, well, it's easy to understand, everybody's going to recover the same value as the sender sent. But even if the sender is dishonest, we still require everyone to recover some consistent output, even though this output might not be the same as the sender input. Could be different value, could be simply a bot. To give you a heads up, why we need to insist this recastability is that obviously we're going to take these two sub-protocols, one put in the beginning, one put at the end. And in the middle somewhere, potentially a MVB would be invoked. Well, as we know, MVB might output some value coming from some malicious party. In this case, we need to deal with a potentially malicious sender. So they cannot mess up with the protocol to violate agreement. And another challenge is we have to strive for minimum complexity, essentially, and for all metrics. The whole reason we need this dispersal idea, we want to reduce communication, but at the same time, we don't want to blow up any other metrics. Somehow we might immediately have a question. So since like a dispersal recover, why not use something more classical, more standard called AVID, asynchronous verifiable information dispersal? Well, if you look at more carefully, AVID actually has a strong requirement on agreement. It says that whenever a party has a valid share, whenever an honest party has a valid share, all other honest party will also have a valid share. Essentially, they have to enforce this recoverability by default and upfront. But this is already like a reliable broadcast. We'll immediately incur n-square message complexity by one single invocation. So in our protocol, obviously, we will have n invocation of this AVID. Then it's gonna blow the message complexity up to cubic, while all the existing protocol only have a quadratic communication complexity. But still, we need some kind of a delayed agreement at the end, like modeled as recastability. So we have to generate some kind of proof to facilitate this functionality. But this proof have to be very short. So the structure of the dispersal phase is extremely simple. All the magic is actually contained in the encoding phase. While the encoding phase and acknowledgement. So basically, the sender will disperse his value to become shares and also some auxiliary data to everyone. Then everyone simply acknowledge he receives a common digest. Well, I will mention what is this digest immediately in the next slides. And the acknowledgement essentially is a partial signature on a threshold signature. Then the sender can compress them again to get a digital signature on a common digest to form a proof we call lock. So once we have this lock proof, actually we can already enable this recastability. So to see this, suppose one honest guy sees a valid lock proof, which essentially means at least f+1 honest guy already signed on the same digest. Otherwise, they cannot compress them to get the threshold signature. And more importantly, so this consistent digest, there cannot exist two different type of consistent digest that is signed by two different group of F+1 honest players, because they have one common guy overlap by applying the simple pigeonhole principle. If any honest guy find the two different versions of a digest, they can immediately report and abort. Now, the party seeing a log proof is confident that he can simply use the log proof to go ask for other people for the corresponding shares. And as long as he can select according to the digest, and he can check whether the share is consistent, then he can take the corresponding ones and recover. So one immediate question appears is that we need a new way to check whether the share are valid. So this will be take care in our encoding procedure. Whenever the sender, before he disperse, he encode the message by using erasure code or information dispersal scheme, get a vector. Then he needs to first commit to this vector. This commitment will be the digest we just mentioning, and of course the corresponding share to the party. But more than that, we also need to provide a proof. This proof attests that this corresponding share is indeed the one committed in the vector in the right location. For example, M1 indeed is the first element that committed in the vector. So we call this kind of commitment position binding vector commitment. The key feature we need is the proof needs to be very short. Actually, we don't really need the commitment to have the normal hiding property, or we only care about this binding property. And one more requirement is that we have to make sure the commitment scheme is actually deterministic, so that everybody gonna have the same digest. Then they can apply the threshold signature to reconstruct the log proof. And fortunately, satisfying the commitment, satisfying all those type of properties can be derived from a cryptographic scheme called a vector commitment. They commit to a vector and enable one to efficiently prove every element is positioned in the right place. And the proof is only has a constant size. Some of you might immediately get an idea of using Merkle tree. Well, Merkle tree do satisfy the functionality, except the efficiency of the proof is slightly larger, which depend on the number of players and logarithmically. Now we have seen the main feature of this encoding scheme. We can quickly analyze the efficiency of the dispersal and recast phase. So in the communication, total number of communication cost is a dispersal and the multicast of the proofs. Those proofs actually are all constant size. So the total number add together is only linear to L plus lambda n. Well, message, the key here is every proof needs to be short, and also the threshold signature is also one of them. And the message complexity is also easy to see. We just have two multicast. So the message complexity will only linear to n in one proposal. Of course, in the recast, it's the same thing. Essentially, I ask for all the corresponding proof and the shares. Now we are ready to describe our protocol of the MVBA extension protocol. Once you understand this dispersal and recast procedure, actually the extension is quite straightforward. So first, every player are gonna disperse his value using this dispersal protocol, and each of them produce a log proof. Once they have the log proof, they're gonna use the log proof as the input to execute the underlying MVBA protocol. So the MVBA protocol gonna pick one of the players' log proof, as we just show because of the recastability. Anyone sees a valid log proof, he's guaranteed that they can all honest player will be able to recast a consistent value. If it's already satisfied predicate, great output. If not, then repeat. And we can also easily check the efficiency here. The efficiency, as we just saw, since now we have an execution of the dispersal phase, essentially just multiply the linear factor to L plus lambda n. We get Ln, the Ln term here. And also interestingly, now because the underlying MVBA is invoked using input only with only constant size, essentially just a log proof, then the complexity will sharply drop, essentially replace the input size L to be lambda. And put them together, especially when we instantiate with Abraham et al.'s protocol, we can bring all the complexity down to Ln plus lambda n square. And also easy to see the message complexity gonna remain the same as n square, and the running time gonna be constant as well. And unfortunately here, even though it's an MVBA extension, reduce the complexity of the underlying MVBA, but in order to get our optimal complexity, the only thing we can use here is still due to Abraham et al.'s protocol. If we run Cachin et al.'s protocol, still the n cubed term is there, make the total complexity still n cubed. So for this purpose, we also make another reduction to binary agreement. Well, this makes the protocol much more complicated, and we need to augment the dispersal phase to make sure the consistency of the recover, because now we're only running binary agreement. We don't have the luxury of MVBA to directly output one of them satisfying the predicate. But the total complexity is also easy to see, because now the election and the binary MVBA only give you a lambda n square complexity. We don't need to see the black MVBA as a black box. If you are interested in the details of this reduction, I'll refer to the details in the paper. So now let's look at again our complexity, and we would like to see whether how far it's close to optimal. Well, the running times, obviously, every of this protocol is actually optimal, it's trivial. And also for message complexity and word complexity, they also match the known bound proven by Abraham. I think it's Abraham et al. And the interesting part is the communication complexity. There's actually a trivial lower bound for communication, because at the end of the day, the protocol needs to output one value. This value has to be multicasted to everyone, so there's Ln already. So if we do a careful calculation where L is moderately large, all the term communication collapse to the Ln term. So the communication will be optimal with a moderately large input size. And the most interesting feature of this complexity reduction is that we can now automatically resolve the open problem of atomic broadcast by running Cachin et al.'s reduction. And we reduce the communication complexity in the atomic broadcast there. Before the end of the talk, I would like to summarize a bigger picture of a practical asynchronous atomic broadcast. And we know the reduction from atomic broadcast to ACS, but there are two different ways to construct the ACS. One is given by Cachin et al. From MVBA, and another one passes from reliable broadcast and a binary agreement. Actually, the latter approach was preferred and picked by a recent work, which is quite impactful work of Honey Badger BFT, because they consider MVBA is the bottleneck of constructing ACS because of the large communication complexity. But our recent results actually kind of refutes this view. And this work we show how to reduce the communication complexity of the MVBA itself and also the resulting atomic broadcast. And in another recent work of us, we show a better reduction of ACS to MVBA, and even in that reduction, actually even use Cachin et al.'s MVBA, the resulting atomic broadcast will still be much faster than Honey Badger BFT. With those Dumbo protocols at hand, we can confidently reclaim that MVBA is still the right way for constructing ACS and atomic broadcast in the asynchronous network. Thank you very much.